Hi, welcome to this discussion on the DMP protocol. Basically, I'm going to talk about an open protocol. What's an open protocol? How did it come to life? How did it make it through the histories? And one of the most important open protocols next we will discuss is why we use the DMP open protocol. Then we're going to talk about the DMP standard by itself and what are the parts of the standard, what do we need to focus on the standard when we're studying the D20 platform. We'll talk about the DMP stack and the contents of that stack, what are the different layers in the DMP stack, how does it relate to the OSI stack. And then we'll talk about the level of support in DMP and how does it identify different point types, how does it refer to point types, how does it communicate those points and data from the field. The two final sections will include the D20 DNP implementation. So how do we take the standard DNP and put it in a D20 platform? And the final section will show you a message of exchange between a master and a field device on DMP protocol. Okay, so let's get to the first section on the open protocols and how did it happen. Through the history of supervisory control and data acquisition, SCADA, many closed protocols were developed by professionals in the field of SCADA or control and automation. And these protocols were utilized in order to allow one device or one intelligent electronic device or IED to communicate with another intelligent electronic device. Soon it was found that one device has to act as a master, sometimes referred to as a client, right? And the other device has to act as a server or a slave device. The word master-slave has been dropped over the years, but is still in use in some of the standards. So when we hear master or client, or we hear server or slave, it's the same. And the protocols that were developed by all the companies were basically closed protocols. By closed, it means it's not shared between one vendor and another vendor. Around the 1990s, there was a need to develop or come out with shared protocols. A protocol is basically all the semantics, the laws, the checks that take place on the messages that's exchanged between the two devices. So there was a lot of efforts in order to develop these protocols. For example, one of the good well-known efforts was written in the thesis of the Basic 4 document on the road to utility communication architecture, and basically started discussing how DMP protocol, which is shared among many companies, will be utilized. A leading company in the field of SCADA, part of GE Wastronic, started to develop the GE DMP protocol. The first versions of the DMP protocol, version 1 and version 2, were not shared. Version 3, sometimes referred to as DMP3, between the year 1992 to 1994, started to materialize and get released. During the same time, there was other efforts to develop other open or shared protocols. For example, the IEEE UCA protocol or Universal Communication Architecture, which was led by EPRI, was in development. The Electrical Power Research Institute was in development. and the IEC 6870-5, earlier known as 8870-5, was also in development. So of course, because all of these protocols are in development at the same time and being discussed among professionals, they used to overlap in functionality or overlap in implementation. So we will see a lot of common features among these protocols, but at the end of the day, they're not the same. So DMP protocol is not the same as 870-5 protocol, okay? And it was an open protocol, a shared protocol that came out around the year 1993 with the first shared released protocol to all the vendors. With the shared protocol being available and many others, the question is, why DMP? Why do we use DMP? DMP was developed as a result of all the knowledge that Westronic, or what used to be known as Westronic and today is GE, as a result of all their gathered knowledge in the world of SCADA and automation. So there is a lot of benefits that exist in DMP. Select before operate, broadcasting of messages, quality information that's constantly exchanged between the device and the master, or the device and the client, informing of all the different information about the device. Also came out with new ideas that weren't common in the closed protocols. For example, unsolicited messages. So an unsolicited messages, it means that before DMP, only that the master was always aware of what message is going to receive as a result of a polling that's sent by the master. An unsolicited message is what we call peer-to-peer communication, where a device will send information even though that information was not requested as a result of an event or a result of a change in data that the device has been programmed to report to the other device or to the master. So this opened the way for other open protocols to start implementing something similar to an unsolicited message. So all of these great features, time syncing, which wasn't a strict thing that's available in a lot of other devices, level of support. So devices could be at level 1 DMP or at level 2 DMP. And pay attention to this. DMP version 3, right, is referred to, sometimes the V is dropped, so we say DMP 3, and then the level of support of the device. So you have DMP 3-L1, that's DMP 3 device level 1, and DMP 3-L2, the DMP 3 level 2. And that means that the device has the ability not to include all the information or support all the codes in DMP, but can have smaller implementation of DMP. This made the protocol or the standard very flexible and widely adopted. And over the years, against all the criticism that was provided with the overhead and the checks and the type of message, DMP has proven to be very, very trusted, and comes with a high trust support from any implementer, and as such has gained a wide adoption among SCADA implementers or SCADA vendors. So now that we understand how this open protocol came to life, let's talk a little bit about the DMP protocol, distributed network protocol, and what have been produced over the years, and how did it evolve over the years to become what we have today, which is the 2012 IEEE standard released today. And probably it will keep on improving and evolving over many coming years. Okay, so over the years, the DMP 3 or version 3 protocol came out in 1990 to 1994. Was the release of the protocol, and many items were resolved with the users via the DMP users group who adopted the DMP protocol and started to service the users and the testing process. And then in the year 2010, standard 1815 was released by the IEEE, and this was like the second formal release of the standard. And by the way, the image is not that far from reality. I mean, the standard is really very thick on release, but that's because I think it's very good. It does really handle everything from history to a very clear documentation of every message and what's the expectation of the message going from the master and the reply from the devices. Another release took place in the year 2012, and probably it will keep improving over the years. One thing to note is, regardless of how big the standard is, it cannot handle every situation available. So one of the common things that's in everybody's mind these days is security, right? And there is lots of criticism around DMP and DMP implementation, as far as it's easy to break the message or hack into the message and whatnot. But let's remember that when this protocol was created in 1990s, the security was not in everybody's mind. That what was in everybody's mind is to have this open, shared protocol that gains a great adoption. And even today, there is, depending on who you talk to in the industry, they might say UCA 61850 or IEC 6870-5 or DMP. So even today, the adoption is a little bit still not clear as to what's the best protocol. So the standard is great from covering all the communication and the parameters of communication and the security requirements, and I think it will keep improving for years to come. Just to gain a deeper understanding of the standard, why don't we take a look at the stack or the DMP stack and the contents, how is it built, how is the application laid out, and that maybe will help us understand more of the standards instead of just reading the 1,000 pages in the standard. Most of the protocols define the communication between one application and another application, or layers, what we call as layers, in the Open System Interconnection, or OSI. That made it easy for one application to focus on its task and make sure the task is done properly, and hands off the message to the next layer once the message is complete and ready to be transmitted. Now, the OSI has 7 layers, and the DMP group decided to use the EPA, or the Enhanced Performance Architecture. As you can see in the picture, the EPA has 3 layers. There is the application layer, the data link layer, and the physical layer. Each one of these layers can be broken further. For example, there's people out there that would tell you that the application layer has a layer above it, which is the user layer, or the link layer has a layer inside it, which is the transport layer. And that's true. There is other layers that will show up in DMP as communication requirements show up in the field of communication. But at the end of the day, the adopted layers by the DNP protocol was the EPA layers, right? And that's the application, the data link layer, and the physical layer. If we want to discuss some of the new layering that's taking place in the field of communication or the new stack, what you will find is inside the application layer, if you're complying to a level 4 device, you will find an extra functionality built into the application layer, or an extra layer if you like, which is the DMP Secure Authentication, DMP 3, or this is DMP version 3, Secure Authentication layer. Also, like I said, in the data link layer, you might find there is a DMP transport layer. So the new stack will look something like this: the application layer, including the secure authentication layer, and then a transport layer, and then a data link layer, and then a physical layer, which could be either a serial physical layer or an internet protocol suite layer. As we discussed, that the devices will have some of these layers, not all of these layers, and it all comes down to the implementation of DMP in that device. So to ease up the implementation of DMP in that device, we have talked earlier about levels of compliance to the standard, or levels of adoption in the standards of the messages that are available in the standard to be implemented by the device. The DMP3 protocol will keep on improving over the years. Many messages were developed in order to service the community of DMP users group needs. So, for example, today there is 147 messages available, and it covers everything from the basic communication of just give me a status of a point with no time reference, to authentication that this is a trusted device, it can send and receive messages. And that's about 147 messages to comply with from the master. So the master has to process any message that's part of these 147 messages to be transmitted and received. And what you will find is that this is the maximum, or the level 4 as of today. There will be probably new levels introduced in the future, and the simplest level was a level 1 device, and in a level 1 device the support was only for 36 basic messages, right? So the levels change. At the end of the day, let's not forget the aim of the protocol is to transfer data and information. The information is referred to as metadata, or information about the data. For example, what is the point online or offline? Does the point has a time tag with it or without a time tag? So all of this was required in order for full functionality of communication to be achieved between two intelligent electronic devices, one acting as a master, the other acting as a slave. One of the key things in communication in DMP is how do we refer to the data that's being generated, a voltage measurement, a current measurement, a status of a breaker. All of this information that is available in our substations is basically translated into digital data, either a digital input or a digital output, an analog input or an analog output, a counter, or a status of a device. And this information is referred to with an index. So the data has an index. The breaker 1 is referred to, status is referred to as the DI1, right? Digital input 2 would refer to another status, maybe of the same breaker or a different breaker. But what we end up with is a grid of information that basically points out an index to every piece of data or information in the field coming from the field is built into this grid of informations that is transmitted from the primary devices in the field to the secondary devices in the field to all the way until it reaches the control centers as information transmit over DMP. The data was not only put in indexes but also in groups classification. So let's say you want the critical data or the class 1 data, or you want the class 2 data, which is less critical, or you want the data that's just a measurement that doesn't impact your day-to-day transaction but is just to keep and make sure that the integrity of the system and the information required for your clients is available. So grouping was just a method of classifying or allocating the data generation. One thing that the protocol works on is object variation and quality. So any data that's generated should be placed inside an object. So it's just an encoded representation of the point. And that data could have many variations. So we could have 32-bit integer value with certain flags, or 16-bit integer value with a flag, or a 32-bit integer value without any supported flag. So the flags were information or metadata that would say whether the points are online or offline. So let's take an example. If I say the information from the field is showing that the breaker is open, right? Or status is the digital input value is 0. Is it 0 because it's really open? Or is it 0 because the monitoring point is offline? So that's why this extra data is important to us as monitors of the SCADA system to take the right action, that we're not just looking at the value of the data, but we're also looking at the status or the quality information of that data that we're receiving. Now that we understand the data that's being transmitted between two devices, what kind of messages can we transmit between the two devices? What's the classification of these messages? So in the standard, they say there is 3 types at this point. There's a confirmation message, a request, and a response. The confirmation message is a message that's sent between the master and the outstation, telling or informing the device in the field that the master has received the message, and this confirmation is sometimes handled at the data link layer, and it could be handled by other layers, but it can be turned off if the device does not require this confirmation message. This is a common thing for me in the classroom when students are looking at the messages between two devices and they see a lot of confirmation or enter messages between the pollings. And they go, well, how come there is an extra message in every polling? Well, that's because for every message, the master is sending a confirmation message. A request from the master to a server or a slave device could include either a read, a write, a freeze, or an immediate freeze. an authentication message, a file handling message like open a file, get a file, request, or a restart message. So the device is being requested to do a cold restart or a warm restart, or a clear of certain statuses like a clear of a freeze status. The message is permitted by the standard as a reply from the device or the server to the master. Will have the value of either 129, which is a hex of 81, and that's basically just a response to a request by the master. Hex of 82 or 130 would be an unsolicited message, and that's a response without a request from the master if unsolicited is enabled, and the master has the ability to listen or ignore unsolicited messages. I get asked this question is why would the master wants to ignore unsolicited messages? What if there is a device in the field that you can't service in the near future and it's just chattering unneeded unsolicited messages? Then you might want the master to just ignore the messages so that it's not raising false alarms, which is one of the annoyances that come with a SCADA system. And the last type of messages that could be responded is hex 83 or 131 decimal, and that basically is an authentication response that's part of the security buildup. Now, every message there is the I to N bits, or the internal indications bits, and those internal indication bits come is basically 2 octets, as you can see in the picture. Each bit in those 2 octets have a meaning. So it's either tell us that there is a class 1, 2, 3 data that's available for scanning, or it tells us that the device has received a broadcast message. And there is some important bits that will tell us that the device is occupying a trouble state, or the device receives an unknown object, which means an unsupported message, and or it has a buffer overflow. So those I to N messages are basically utilized by the master in order to manage what polling needs to happen to the device, or inform the person who's taking care of the system to dispatch the right engineer to take the right action at site with that device. And depending on the device, maybe the device require a restart. It might be handled remotely, or it might need to be handled physically at site. So these I to N bits were defined in the standard as an important part that will tell us about the device status and some quality information about the device. So we have a good understanding of the messages being transmitted between the master and the server or the slave device, and the type of objects. This brief understanding can be complemented by a reading of the standard if we want to get deeper into the protocol. In the meantime, I'll try to show you how the implementation of the D20 communication or the D20 platform of the DMP standard took place. So in the middle of the picture, we see the device, the remote terminal unit that's between the master station and the IED in the field. The remote terminal unit has the application architecture that will allow the storage of information until requested by the master station. Okay, so let's start the journey of information or data through DMP via DMP protocol from the IED all the way to the master. When an event takes place in the field, it's recorded by the IED, and that data change or event will be formulated in a DMP message based on the DMP standard, and then transmitted to the physical port connected to the IED. So now the message is at the physical port that's connected to the IED and is monitored by the physical application layer. In the case of the D2X platform, that will be either application B013 if the physical port is a serial port, or B052 if the physical port is a network port. Once the physical application integrity of the message is checked, it will take that message and pass it to the data link layer. In this case, the data link layer is application B015 or bridgeman. The bridgeman will check the source application ID or application address, that is the IED application address or DMP application address, and the destination application address, and the physical port through which this message should be transmitted. If the message meets all the data link requirements, the message is then formatted and transferred to the application layer that handles field devices. In this case, it's B023 or the DMP data collection application, which is DMP DCA. The DMP DCA basically picks the facts or the point status, the digital input 1 status, digital input 2 status, digital input 3 status, analog inputs, and store the information in the database, in the main database, or our WSDAC interface node or WIN database, application B008. The information will then travel to the application that is requesting the information, which is B021 or DMP data processing application. The DMP data processing application layer will format the message and send it to the data link layer, bridgeman B015, which would check the integrity of the message, check where the message needs to go, and format the message, forward it to the physical application layer, which is B013. As you can see, as we're talking through the layers, the EPA layering is met from application to data link to physical layer. Now the physical layer B013 has a fully well prepared message that can be placed on the physical port. Well, depending, that physical port could be either a serial port or a network port. So once the message reaches the physical port, it travels over the physical media that's connected to the master station. The master station will process the information that's received from the D20 RTU and take the applicable actions, whether to show it to the operator who's monitoring the master station or to send a required programmed command. Okay, hopefully this gives you an idea of the flow of information from the IED to the master through the RTU over the DMP protocol. Other applications can pick up the DMP protocol information from the WIN database or the B008 application or database that basically stores all of this information. So the information can be transferred either to a DMP master via the DMP application B021, or if there is a different master that is talking a different protocol, it can be transferred to that master also, as long as the data processing application that's servicing the other master is enabled and picks up the information from the WIN database. In order to get a good understanding of the messages and how do they get transmitted back and forth between the master and the IED via the D20, I've made a small capture of the communication between the D20 and an IED, and I'm just going to show you a deciphering of that message, basically a breakdown of that message. Okay, so I'm using a DMP translator, and basically I've captured the three messages, one from the master to the slave, and an acknowledgement from the slave to the master that the message has been received, and then the response from the slave to the master with the message. So let's start with the message from the master to the slave. The message is basically three layers. So you can see there is the data link layer, which is the top part of the message. And a DMP message always starts with 0564. As you can see in here, 0564. So that's a starting of a DMP message. The next thing that you will see is that the length of the message. So we can see 14 in hex or 20 in decimal, and that's the length of this message. After that comes the control part of this message, which is, it tells us that the direction of this message is from the master to the outstation or to the secondary device. Okay, and some of the bits which can basically tell us about the controlling version and the function code that is being requested. Then we have the destination address, which is 50, the source address, which is 100, so 6400. That's the destination address and the source address. So this is a 20 length message, and it's from the master to the slave, and it has a destination address of 50 with a source address of 100. And then comes the cyclic redundancy check for, or the CRC for the header part. So in this case, it's saying that cyclic redundancy check is valid. On the transport layer, its only responsibility is to assemble more than one frames or multi-frames into a single frame. So in here it's saying this is the first frame and this is the final frame. So no additional frames are added to the device. And there is a counter for the message. The most important piece is the application layer. So this is in reverse of the stack that we discussed earlier, where you have the data link, the transport, and then the application layer. In the application layer, again, we start with a control, which basically tells us that this is the first fragment and the final fragment of a message. And the sender is not expecting confirmation, which is the master in this case, and we're sending a read request function code 1. All right, the user data, we can look at the translated data. So the translated data says this is a class 1, 2, 3, and a class 0, object 60 variation 1. So we are doing an integrity check, which means there is no range. Send me all the objects, all the points that is available in the target device. The next thing we see is a data link layer message. It has no application layer or a transport layer part. And basically the message size is, of course, it starts at 0564, and the message size is 5 bytes. And then we start with the control, which tells that this is from the master to the secondary station. Right, from the master to the secondary. This is from the secondary station to the master in the direction of the master. And the destination address is 100, the source address is 50 with a valid CRC. Okay, then after that, we receive the answer from the device. And if we look at the translated values, as you can see, it only says 0.0 is 0, 0.1 is 0, 0.2 is 0. Now it's only sending the status of the points, okay? And it's sending that the first point index number is 0, the second, the last index number is 2. One thing to note here, the naming of the points doesn't get transmitted with the message. So you have to make sure that the name or the tag name is the same name or is what your operator is expecting to see in the point display in both the master and the server device. Okay, so hopefully this gave you a good understanding of what goes on between the master and the device with an acknowledgement, which is constantly repeating in a substation based on a polling duration that you pre-configure in your substation. Okay, so to recap, we have covered the DNP protocol, its history, how the stack is laid out of the applications, get you familiar with the applications that are available and how the messages compare to an OSI layer message. And finally, we've shown you a breakdown of a DNP message. Again, it starts with 0564, and then you got the destination address, the source address, the function codes, all built into this message. One message that comes from 3 layers back and forth between the master and the device or the slave device. Hopefully you had a good learning and hope to see you in future learnings. Thank you.